Okay, hi everyone. This is Chenner McPhees from Nutshell Concepts, and welcome to our third video whereby we're designing and building a self-sustained electrical system. And in the first video, we pretty much did our circuits and designs and sized our devices, and eventually we came down to buying the components, and now we have it all and we're ready to build. In the second video, I introduced those components to everybody, and now we're gonna try to put it all together. But before we do that, I just wanna give do some updates based on some basically some corrections, and based on what we ordered, and based on the goal of the project. So I'll start with the fuses. In the first video, I'd logged in a lot of time, and when it came to identify the sizing of the fuses, I kind of rushed through that. In the process, I kind of swapped the sizing of the fuses, and whereby the fuses between the solar module and the charge controller should have been 7 ohms. Based on calculations, I had called that 10 amps, and then the fuse between the battery bank and the inverter, I'd called that a 7 amps. So let's do a quick correction on that before we move to actually building this, alongside a lot of design changes based on the actual ratings for the components that we got. We were able to find online to match our design. So for take for instance, we now know that this guy should be a 7 amps, but however, I had mistakenly used an with a maximum current, right? Or maximum current or maximum power at maximum power, but that would not be the right guy to use in fusing. That actually should be short circuit current. Short circuit current is a current at no load, so it is higher than uh, than a maximum current. I know that says maximum is kind of counterintuitive, but yeah, short circuit is no load current, and therefore it's more than IMP. And when you do that, you account for you account for the oversizing correction factor, which we talked in the first video, and also the irregularities of the panel, which in other words is the over irradiation, which we also talked about in the first on the DC side. So when you multiply that, it gives you 7.57, which leads to 8 amps, right? But since we're using a 12 number 12 wire, which can carry nominal voltage, can carry like 20 amps, everything being equal, we can go to 10 amp fuse. So I'm deciding that we should use a 10 amp fuse for this guy right here. Now for the fuse between the battery bank, and we also should put a fuse between the charge controller and the battery bank. Now I put the fuse between the charge controller and the battery bank is simply the charge controller amperage, which we got is at 6 amps, if we remember clearly, multiplied by 1.26, right? So that's 6 amp, or 12 volts, 6 amp charge discharge, steady charge discharge. It gives you 7.8. Again, that is 8 amps. And of course, since it's a 12 amps again, there's no reason we can't use a 10 amp fuse. Now, when it comes to sizing fuses, well, you have to understand that we're worried about the power eventually, because with power, power is going to try to stay the same. That's the way electricity works, right? So if you increase the voltage, the current will go down. If you increase the current, the voltage will go down just to match the same level of wattage that is being consumed. So what we're really worried about is current. And so high voltage actually benefits us, but when the voltage goes down, there's a surge. The current goes up. We want an amp. We want a fuse that will burn out rather than have the wires melt or arc and cause some kind of fire. All right, so we got those two, 10 here, 10 there. That'll be great. So now for the fuse over here, this fuse, which we identify as 10 amps, the calculation was simple. We take our 23.5, which we identified at the bottom here, 23.5 amp hours. We divide it by 3 continuous hours because that's the continuous hours. Remember, this is amp hours. So if we're dividing this by 3, for the continuous hours according to NEC code, that will give us the actual current, right? And then you multiply that current by 1.25 correction factor again, 9.7. So basically another 10 amp fuse here. So that would have been fine. For this guy here. But what we also have to consider is that when you're sizing for fuses, you want to make sure that you're sizing for max current anyways, right? So we use the 23.5, which is what we designed for, but when we ordered, we could only find 26. The closest we found was 26 amp hours, right? So we should use the 26 amp hours to size, right? So the battery amp hours divided by 3 continuous continuous power for the system will give you the current. Now 23, that is 8.6 amps. Our fuse rating will be 8.67 amps times 1.25. That is 11 amps approximately, and we more likely not find an 11 amps. You'll find it 15 amps. So we'll go with 15 amp fuse rating for this fuse, rather than well, this would have been a 10. Now we know based on the new battery size capacity that this would be a 15. So we will this will be 11. So we'll go with a 15. All right. So that takes care of that. So what else did we also do here? Yes. Another thing we did was, remember we had the 75 watts. We projected the 75 watts. We proposed the 75 watt. We eventually got an 80 watts. So that correction is in there. Doesn't really do too much change to anything in the system. We're still going to the 12, number 12 wire. In both cases, in and out. But here we had proposed 10 wire. We raised it up because when you're dealing with an inverter that has an output AC that high as 120 to 40, and a batteries really do, sometimes they look like idle objects, but they can really pack some power. It's only right that you really size upwards for protection. So, but I've decided that we should go with a 12 because even though we worry about safety, you really just only want to do as much as you need to protect your system, and if you don't have to spend too much money, because as the wire sizes go up, the cost goes up as well. So, but I'll explain why, my rationale for using a 12 anyways. And that is here where we have we got a 350 watt to cover the surge, even though we knew that we needed between 50 to 100 watts. In this case, 50 watts and 100 watt hours. We tried to cover the surge, and we went between 120 to 200, eventually getting this guy. This guy then changes dynamics a little bit, because sizing for fuses means that when you size with fuses, you do 12, you do one or two things. You consider the source, or you consider the draw, whichever is bigger, right? And so in the first part of our sizing, we considered where the power is coming from, and we get a 15 amps. However, if you're going to take the whole system into consideration, the other way to size for our wires and our fuses here would be the inverter watts divided by input voltage, in this case 250 watts, which is covers for the surge, divided by 12, 29.16 amps. The fuse rating will be 29.6 amps times 120 correction factor, 36 amps, about 40 amps generally. Now, what that means in essence is that our wire will not be a 10 amps, right? Because we talked about this in the first video. It will not be a number 10 wire. It should be a number 8 wire. And when I looked at the manual for this guy, it seems to be in line with what I'm saying, because they recommended number 8, and then they recommended a 50 amp fuse. However, we have a system, a really small system. We run a 12 volts coming out of here. We have a 6 amp basically discharge going through here. This is not a big system, and the draw, and we have these loads. We know that this is a load that we're sizing for the system for. So even though, yeah, we will be meeting a higher level of safety by going with 8 amps, given the system we have right here, given the low voltage, given the low current draw, there is absolutely no reason why we cannot stick to having a number 12 wire here to guard for, which would more than cover for whatever draw we're getting out from the DC side. At the same time, also not worrying about the surge, which is why we decide, which is what this extra wattage on top of what we know that we need is for, which covers for the surge. We don't anticipate such a surge from a system like this. 12 volts, 6 amps, 80 watts, not likely. So a 12 will save our money and still maintain safety. With all the fuses that we put in place, should all cover our anticipation without being afraid that we are violating any core safety principles over here. All right. If we decide to go bigger and have a bigger battery bank, and even at 80 watts, we want to have a bigger battery bank, or we want to upgrade and actually use string systems, right, whereby we have solar models or solar panels connected in series or parallel to increase our capture, irradiation, and so therefore increase the amount of power we can generate at the source, and also come here and connect batteries, increase the size of our battery bank from one battery to 2, 3, or 4 in series and parallel, then definitely this guy will come into play. But for the simple project we're doing right there, I think it's safe for us to go this route, save money, and go with a number 12 wire, and the fuse calculations we have should do as well. So that brings us to the last part of this project, which is to build. We have all the components which I showed you in the last video. We have done an update of our design. This is what it's going to look like. I should mention also that I decided that it's also for safety purposes to introduce a switch. It's gonna be a DC switch if I could find one. If I can't find one where the switch is a switch, I can use an AC switch given the low voltage. If I get an AC switch with that can function for a high amperage, it will cover, DC, AC. Like I said, if I use an AC switch rather than a DC switch, an AC switch, AC is alternating current, and it will have a point where it goes to zero. And what we're afraid of with a direct current never has to do that. It goes straight through, right? So if we have alternating current that will eventually go to zero, if you're running direct current through a device that actually is rated for AC current, you now run the risk of a time where this direct current never has to go to zero. So you know that it's possible that some irregularity in the system can cause heat, arcing, and we don't want any of that. But this is a very small system, and if I have an AC switch, if I can't find a DC switch and I get an AC switch high enough, a factor of 1.8, usually people, I've seen people use that. Usually people 1.8 DC, AC to DC. Maybe I can get away with it. And worst case scenario, because it's such a low voltage, if this is 120, if I get an AC at 120 volts versus a 12 volt DC, worst case scenario, the switch, if it has an indicator light, won't go on. But the switch is a switch; it just throws. So I decided that we're going to use a switch for safety purposes. So I can cut off, or we can cut off the DC side if we need to, without things just continuously keep running through the wires and through the devices. We have a way of actually safeguarding our system and separating one side from the other and controlling it. All right. So, like I said, our next designation, next point of or port of call will be to build. That'll be exciting, and join me when I do that in the next video. All right. Thank you so much. Bye.